Welcome to Lab 10 Part 1, where we will cover numerical integration using the midpoint rule, the trapezoid rule, and Simpson's 1/3 and 3/8 rule. In this video, we will be using this integral as an example. Before we start, we must first import all of our libraries. So here we will need NumPy as NP, SymPy as SP, Pandas as PD, and matplotlib. Then I will declare a function f with the input x to return our equation. And our equation is 2 plus 2 times x plus x squared plus numpy dot sine of 2 times numpy dot pi times x plus numpy dot cosine of 2 times numpy dot pi times x divided by 0.5. Before we use our rules, we will first evaluate the integral using SymPy's integrate function. To do that, we will need a SymPy symbol, which we will call x, and then our SymPy expression y. Let's go and copy our equation. And then I will convert all of our NumPy functions into our SymPy functions. And then I will call SymPy's .integrate function, pass in our expression y, brackets, and our interval, where x is the variable, and the interval goes from 0 to 1.5. I will set the result to I true, and then convert this into a number using SymPy's n function. And I will print out I true. Here we see that the integral from 0 to 1.5 is 6.693. Next, I will graph the function. To do that, I will set x values equal to numpy dot line space from 0 to 1.5. Then using plt dot plot, I will plot the x values, call our function f and pass in our x values, and then plot dot show. And here we have our graph. Next, we will cover the midpoint rule. The midpoint rule approximates the integral using rectangles with a width of h and a height that is the average of the current point and the previous point. We will first define our function as Im with the inputs f, our equation, a, the start of our interval, b, the end of the interval, and n, the number of rectangles. Then h, the width of each rectangle, will be equal to our endpoint minus the start point, which gives us the width of the entire interval divided by the number of rectangles. Now we will return the summation shown here, which is h times the summation from 1 to n, and the body of the summation is f at xi minus 1 plus xi divided by 2. That will look like h times by the summation. We will use a list comprehension. Then we will call our function f, and we must start at the starting interval of a plus xi minus 1, which is I times h, which is an ith number of step sizes of h, and minus h since this is xi minus 1, and then plus I times h, which is xi divided by 2, and then for I in the range of 1 to n plus 1. And then we will test our function, Im, pass in f, starting at 0 to 1.5 with 15 rectangles. And here you can see our approximation, which is fairly close to the actual result. To increase the accuracy, we can increase n, the number of rectangles. To see the effects of increasing n, we will draw a table. So here we will set table to an empty list, and then do a loop for I in range of 1 to 5, and we will change the value n by a factor of 10, so 10 raised to the power of I minus 1. Then we will see the effects of n on our function, so our approximation will be equal to our function Im with the inputs of f, 0, 1.5, and n. Then we will append this to our table as a list, where first we have n, then we have the width h, which is 1.5 divided by n, then our approximation, and then our error, which is the absolute value of I true minus our approximation. And finally, we will display our table as a Panda data frame, pass in table, and the columns will be n, h, our approximation, and our error. Here you can see as we increase the number of rectangles, our approximation gets closer to the actual value, our error decreases, and the width h also decreases. Moving on to the trapezoid rule, suppose that we have an n of 3, which means we will split our function into 3 segments. The trapezoidal rule relies on linearly interpolating between points and then finding the area of the resulting trapezoids. Now I will declare a function as it, f our equation, the interval from a to b, and then n the number of trapezoids. And then h, the width of each trapezoid, is the ending interval minus the starting interval divided by the number of trapezoids. Next we will return the summation, which is h divided by 2 times the summation from 1 to n of f at xi minus 1 plus f at xi. We'll start by multiplying h divided by 2 times the sum of our list comprehension. Then we have the term of f at xi minus 1, which is a plus I times h minus h, plus f at xi, which is a plus I times h. And then for I in range, the summation goes from 1 to n plus 1. Finally, print out it, pass in f, the interval 0 to 1.5, and then 15 trapezoids. Next, I will copy and paste the code for our table and make some changes. So now we're testing the it function. From our table, you can see at 1000 trapezoids, we get an error of 1.79 times 10 to the negative 6. Moving on to Simpson's 1/3 rule. For Simpson's 1/3 rule, the interval from a to b is divided into n subintervals, and then a midpoint is found within each of these subintervals. And then the points are interpolated using Lagrange polynomials. As a result, in each subinterval, we're integrating polynomials. Each interval contains two smaller intervals, where each of the smaller intervals has a width of h. So the width of each subinterval, which have two smaller intervals, has a width of 2h. Since we know that the width of each subinterval is b minus a over n, this must be equal to 2h, which means that h is equal to b minus a over 2n. So let's go ahead and declare our function as is1 with the inputs of f, the equation, the interval a to b, and then n, the number of subintervals. As we said, h is equal to b minus a divided by 2 times n. And then we will return our summation, which is h over 3 times the summation from I to n of f at xi minus 1 plus 4 times f at xmi, which is the midpoint, plus f at xi. So return h divided by 3 times the summation, which have the terms of f of a plus I minus 1 times 2 times h. And the second term is 4 times f of a plus 2 times I minus 1 times h. And the third term is f at a plus I times 2 times h. And then for I in range of 1 to n plus 1. And then we will call our function as is1, pass in f, the interval 0 to 1.5, and then 15 subintervals. Now using this method is very close to the answer we got using SymPy's integrate. And once again, we'll copy the code for the table and switch out the function for is1. Now we're getting very accurate results, where the error at 1000 subintervals is 8.75 times 10 to the negative 13, and already at 100 subintervals, we're getting a very accurate approximation. Finally, onto Simpson's 3/8 rule, where our interval is divided into n subintervals, and each subinterval has two intermediate points, as opposed to the one midpoint we saw in the 1/3 rule. Now instead of integrating parabolas, which we saw in the 1/3 rule, we're now integrating using cubic functions. So now with two intermediate points, each subinterval contains three smaller intervals, where each of the smaller intervals has a width of h, which makes the length of our entire subinterval 3h. So this means that the width of the subinterval 3h must be equal to b minus a divided by n, which means that h is b minus a divided by 3n. Now we will go ahead and program our function, is2, with the inputs of f, the equation, the intervals from a to b, and n, the number of subintervals. And like we said, h is equal to b minus a divided by 3 times n. Next, we will return the summation, which is 3 times h over 8 times the summation from I to n, with f at xi minus 1 plus 3 times f of xli, which is the left intermediate point, plus 3 times f at xri, the right intermediate point, plus f at xi. So in code, this looks like return 3 times h over 8 times the sum of our list comprehension, the first term being f at a plus I minus 1 times by 3 times h, plus the second term, which is 3 times f at a plus 3 times I minus 2 times h, plus the 3 times f at a plus 3 times I minus 1 times by h, plus the last term, which is f at a plus I times 3 times h, and then for I in range of 1 to n plus 1. And then we will call our function is2, pass in the inputs f, the interval 0 to 1.5, and then 15 subintervals. So here you can see we get a very close approximation. Once again, I will paste the code for our table and change the function to is2. So here you can see even at 10 intervals, we're getting a very good approximation. This concludes the video on numerical integration, where we saw that as we increase the number of n, our subintervals, we got a more accurate approximation, as well as a smaller step size of h and a smaller error. To review, the midpoint rule uses rectangles, the trapezoidal rule uses linear functions, the Simpson's 1/3 rule uses parabolas and one midpoint, and the Simpson's 3/8 rule uses cubic functions and two intermediate points.